Hey there, physics folks. This is part 2 of the warm-up solutions for January 10th. For those of you who could not make it into class today, we went over 2 warm-up problems, 2 work and energy problems. We did the first one in the last video, made the solution here. The second one has to do with a ball traveling down a ramp and then getting launched. So let's go ahead and get right started. Now, I made a larger version of this so you can more easily see it on the video. I do want you to go ahead and try these first without looking at the solution. So if you want to pause the video so that you guys can give it a shot first, that'd be great. Okay, so if you've now come back after trying, you probably found that you maybe got a little stuck, because unlike the backpack where we have a change in energy problem, we ended up being able to solve it with kinematics and energy equally well, or with an equivalent solution. We even reminded you in the last video that these 2 equations, the one that you get solution from kinematics and the one that you get from conservation of energy, end up being the same equations, different variables but representing the same values and therefore the same answers. Now that's not going to work with this ramp problem with the launching ball, because of course if you try to use kinematics, even if you knew some of what's some information about this ramp, let's say the height that we do know, we don't know the angle, so we can't really calculate the acceleration down the ramp using g sine theta. We don't know the length of the ramp, we don't know the time, so kinematics is not really going to help us out here. So we're going to need to concentrate on the conservation of energy to solve this problem. So anytime you see, heights and velocities or speeds changing, it's always a good idea to take a look at the problem through the lens of conservation of energy. So let's go ahead and read the problem. So we have a particle or a ball starting from rest at point A up here in the drawing, is projected down the runway as shown in the drawing. It says projected because they're implying that it has a velocity here. Upon leaving the runway at point B, so now we can assume this is vertical, and it says the particle is traveling straight upward and reaches a height at 4.00 meters before falling back down. Ignoring friction and air resistance, find the speed of the particle at point A. Now, first of all, we can assume that it has a velocity here, and the reason we can assume that it has a velocity is because, of course, if it didn't have any velocity and it just went down, according to the conservation of energy, it would reach the same height. So it has some potential energy here, down to kinetic, and then back to potential. But we know because it reaches a height greater than its initial height, we know that it must have had some additional energy over here. Now, we know that this is its final height because it says it reaches a height of 4 meters before falling back down. So that's its final height. So as always, let's just take a look at the conservation of energy. So 2 types of energy we are always going to discuss in this chapter are potential energy, energy due to weight and height, plus kinetic energy, energy due to motion. And I'm going to say that's the PE at the end point, and this is the PE n plus KE at the starting point. Now, we know that the conservation of energy simply states that the total energy before in the green oval here and the total energy after, vice versa, are always equal. Does not mean the potential energy here is equal to the potential energy here, and it's clearly not because they're at different heights. It does not say that the kinetic energy here and the kinetic energy here are equal, and it's clear they are clearly not because this is stopped and this is moving. But we know that the totals in the green boxes are equal, or green circles or ovals are equal. So PE initial plus KE initial equals PE final plus KE final. Okay, now before we even get started, before I even expand these, I'm going to go ahead and delete the one that I want, anything that I know is 0 for sure. Now conceptually I know because it reaches a height of 4 meters before falling back down, I know the final kinetic energy has got to be 0, okay? And that's got to be 0 because the velocity at this point when it gets to the top is 0. Just like when you throw a ball straight up, the velocity at the top is 0. Okay, so that's cool. Now, before we do any other canceling or any other simplifying, let's go ahead and expand these. So we have mgh initial, you could say at point A if you want, plus 1/2 mv initial squared, that again could be at point A, And we know that there is a velocity there because it shows us, and we know conceptually because it gets higher, it has to have some more energy there, is equal to the final potential energy, mgh final. Okay. Now, at this point, we can see that, yes, indeed, everybody brought mass to the party, so the mass goes away or gets canceled. And a lot of people wonder why that is in energy problems. Well, it's the same reason that all objects fall. It's for the same reason that we know that all objects fall at the same acceleration, regardless of mass. Galileo's law of falling bodies allows these objects to fall in the same way. So the masses will always tend to cancel, especially when we have gravitational potential energy involved in the situation. Okay, now I'm going to suggest, just as we did in the last problem and the problem before, that we lowest height, this lowest height, I'm going to call this my new reference point. So my initial height, I'm going to say, is 0. Okay, so the lowest point that we have the ball represented with something that we know about, because we know that it's 3 meters above. I'm going to call that 0. Now the reason I'm going to call that 0 is because I know I have a change in height. So I know I have a change in potential energy. I go from potential energy to potential energy. It's got to be different because it's got to be at different heights. But by calling the lowest one 0, the lowest height 0, I avoid a little extra mathematics, and I actually simplify my algebraic expression, which I'll show you in just a second. But don't get too hung up on this idea, because what you need to understand is the difference in heights. It really is between 3 meters and 4 meters, and the difference between those, of course, is 1 meter. Now, again, if you're uncomfortable with that, let's just remember that when this ball goes down here, sure, it does gain kinetic energy. It gains a lot of kinetic energy on the way down. Okay, so green, it's gaining kinetic energy. Okay, now it's gaining kinetic energy because it's losing potential, because it's losing this height. However, when it goes back up, when it gets launched and goes up the ramp and then gets projected and goes back up to this point here, it reaches the same height. And it reaches the same height because I shouldn't say that. When it reaches the same height that it started with, it now has the same potential energy because it's the same 3 meters above the reference point. Now, because there's no friction and no air resistance in this problem, and it says so right here, ignoring friction and air resistance, we know that the amount of kinetic energy gained here to the amount of kinetic energy lost here, and the amount of potential energy lost and the amount of potential energy gained, those are all the same amounts. So we can basically just ignore, I don't want to cross it out because I don't want to confuse you guys, but I'll do it in a light color so you don't have to worry about it. But if we can basically ignore everything that goes on below that line, because we don't care about it, because we know no energy is lost. Okay, so with that in mind, I'm going to go ahead and I'm going to cross out my initial potential energy and say that that's 0. And so now I have an expression that's familiar to us as the last problem was. 1/2 V naught squared equals GH final, which of course simplifies to V naught equals the square root of 2GH final. Now what this really says is that this is the speed that you need to have in order to launch itself 1 meter above its beginning point. In this case, we have all kinetic energy at the beginning going into all potential energy at the end. Okay? That won't always be the case, but in this case it is. Okay, let's go ahead and plug and chug. So we get V naught equals root 2 times 9.8 meters per second squared times the height. What's our height? Well, it went up from its 0.1 meter. And that's going to be the square root of 19.6, which is really close to the square root of 20, which is more than 4 and less than 5. And the number, if you plug and chug, you get will be 4.42719 meters per second. Check the units. Yep, they check out. So this is going to be 4.43 meters per second, which checks out with our answer down below. Okay, again, just to not belabor the point, but if you're uncomfortable with this idea of ignoring what happens down here, remember that only can be done when we have no friction and no air resistance. If you're uncomfortable with that, well, let's just try it again. Let's just leave, instead of crossing out that initial potential energy, let's just say that this is that with our reference point as being down here at the bottom, somewhere down here. If we're going to continue this as our reference point, then we have 3 meters up to begin with and 4 meters up at the end. So that means we're going to start out with some potential energy, mgh initial, plus some kinetic energy, because we know it's got to be moving, 1/2 mv naught squared. I know we've already calculated that, but let's just leave it that way. And we know that it ends at some potential energy final, mgh final. Now look at what this says. This says these two buckets of energy, the potential bucket and the kinetic bucket, all get filled into one big potential bucket at the end. And that's in fact what happens. But again, just to illustrate that it's legal, legit, if you will, to call this a 0 point, even if we don't call it a 0 point, if we use the pink line here as our reference, that yields this expression. So let's just go ahead and solve for v in this case. So first of all, everybody brought mass to the party. The m's cancel. I like to multiply everything by 2 to get rid of the halves, and so we end up with 2gh naught plus v naught squared. You can see that's now isolated, or by itself. Gh final times 2 over here, because we multiplied the whole thing times 2. And I'll just go ahead and do that. And if we do a little solution, a little algebraic solution, you get v naught equals the square root of 2g's in both terms times, in this case, it's going to be h final minus h initial. And I think you'll agree that if I circle these both again in red, even though they are different expressions, different values that we're going to plug in with a couple exceptions, you'll see that this HF final was the 1 meter, and we can see that this final, which was 4 meters, so this is just a 4 minus 3, and that's the 1 meter. So we don't even need to calculate this. It's going to come out to the same answer. Again, just to make you feel a little more comfortable about setting that height equal to 0. Okay, feel free to review this again, print out the document, and try these problems again if you're having difficulty, and hopefully that helped you get a little bit more acquainted with the conservation of energy and the power of solving physics problems. Okay, thanks very much. See you next time.